So our second speaker of the day is Nicholas Seeger. He will be presenting his talk on quasi-random influences for Boolean functions. And Nicholas is from University of California, San Diego. Nicholas, feel free to jump in.
All right, thank you for the lovely introduction, and thank you to all of the organizers for this wonderful conference. And as my title slide shows, this is joint work with my advisor, one of my advisors here, and John. So I have a funny word in the title here that you may not have seen before, which is quasi-random. What do I mean by that? So the motivation for all of this sort of topic is that we have a bunch of deterministic mathematical objects, yet somehow they look kind of random. So some examples of these things are things like digits of irrational numbers, expander graphs in graph theory and computer science, pseudo-random generators, similar things along these lines. And they all have these random-like properties, but they're entirely deterministic. So how can we make this notion a little bit more precise? The answer is a theory of quasi-randomness. And it's going to have three parts. First, what we'll do is we'll construct a list of properties or tests that can be used on both purely random objects, but also on deterministic ones. Second step, we'll take that list of properties and prove that they all imply each other and collect the result together into an equivalence theorem. And the rough idea is that each of these properties sort of captures a different form or a different view of this notion of randomness that we're describing. And then we'll construct some explicit examples of deterministic objects which actually possess the properties of our equivalence theorem. So if you wanted to do this for irrational numbers, you'd collect a bunch of stuff together, prove that it's all equivalent, and then prove that a specific irrational number exhibits the properties of the list. In fact, another example, one that got the entire field started, is the theorem of Chung, Graham, and Wilson from 1989. It's going to be defining quasi-random graphs. So I give you a sequence of graphs with 1/2 and choose 2 edges, let n go to infinity, then the following properties are going to be equivalent. So my first property is that if I give you any labeled graph on exactly k vertices, well, it's going to appear as a subgraph of G about as often as it would in Gn 1/2, a random graph where edges are picked with independent coin flips of probability 1/2. My second property is that the 4 cycle is going to appear as an induced subgraph of G just as often as it would in Gn 1/2. My third property would be that the largest eigenvalue by adjacency matrix is linear in the size of the graph, but the second largest eigenvalue is sublinear. My fourth property, that if I give you any 2 subsets of vertices, the number of edges between them is about what it would be in Gn 1/2. Now, taking a step back, what's going on in this theorem is we have 4 different properties, none of which necessarily seem to relate to each other. Yet, the theorem proves that these properties, and in fact about 4 or 5 others, are all equivalent up to some small losses in parameters. And so the idea is that if I give you any fixed graph that satisfies one of these properties, for instance, property 2 right here, which is relatively easy to check, then it satisfies all of the properties. And we can say that this graph, in a very formal sense, is quasi-random. This graph shares X list of properties with a random graph. And I mentioned the third step of the process is to construct an explicit example of graphs that exhibit these properties. And one of the theorems that they prove in their paper is that a Paley graph is random in this sense. So this is the sort of prototype of a theorem that we'd like to prove. And I should mention that other people have gotten in on this sort of work, because you can prove quasi-randomness theorems for subsets of the integers mod n, oriented graphs and directed graphs in general, permutations, hypergraphs. As you can tell, this one took a little while to figure out what the right theory was, and what I will be talking about today, which is the influences of Boolean functions. So what we'll be doing here, we'll be considering the combinatorial object of a Boolean function, and we'll be proving some sort of quasi-randomness theorem. So what is a Boolean function? Well, at a very high level, a Boolean function is simply a map from a set of all binary strings of length n to true and false. This can encode a whole variety of things, and appears in a variety of different fields, from computer science to cryptography to combinatorics. And most of the time when we work with these things, we pick up a specific interpretation for what set of binary strings means and what true and false will be interpreted as. For my talk today, I will be interpreting the set of binary strings as vectors over the finite vector space f2 to the n. -1 will denote true and 1 will denote false. You'll see in a minute why this somewhat unusual choice of convention actually will be quite useful. And as an example, some of these functions, well, the parity function, which comes up quite often in the field, or also known as XOR, is going to take in a binary string of length n and return 1 or -1. And the definition of it will be to add up all of my bits, modulo 2, and if it's 0, take -1 to the 0, just 1, or if it's 1, -1 to the 1 will give me -1. So you can check that this formula right here exactly corresponds to the parity function as we normally would. I'll also have to introduce for each of these properties a few definitions to explain what's going on. So first, few basic definitions. Given a vector in x to the n, I'll define its Hamming weight using absolute value signs to simply be the number of non-zero entries in that vector. And similarly, the Hamming distance between two different vectors will simply be the Hamming weight of their difference. Keep in mind, difference is taken over f2. So what this is really computing is simply the number of positions where these two vectors differ from each other. So as an example, the Hamming weight of 0, 0, 0, 1, 0 is simply 1. There's only one non-zero coordinate. And the distance between 0, 0, 1 and 1, 0, 1 will simply be 1 because there's exactly one coordinate where they differ from each other. And since I've defined this notion of distance, you might suspect this actually forms a metric. Indeed, it does. And we can form the ball of radius k around a particular point, which I will denote by b sub n kx. As an example, ball of radius 2 around the point 0, 0, 0, it consists of these 7 vectors. Okay, so as we saw with our preview with the example of the Chung-Graham-Wilson theorem, what I'm going to do here is build a list of properties, and then I will state the theorem that they are in fact all equivalent to each other up to some small errors. So my first property is going to have to do with the notion of influence. The idea, I pick some specific vector gamma in f2 to the n, and I look at how often does adding gamma to my input change the output of my function. That's simply what I mean by this expression right here, where I take the probability under uniform distribution over all values in x that f of x is not equal to x plus gamma. Now, if I were to pick a uniformly random function, you can check that the gamma influence should be relatively close to 1/2 for every non-zero gamma. And so that's going to be my first property. A Boolean function f will have the balanced influences property, which I will denote by inf k and epsilon. If the gamma influence is close to 1/2, or close is measured by epsilon, for every non-zero vector in the Hamming ball of radius k. You should sort of think that if I change my function, the input of my function by at most k bits, I basically can't predict what that will do. That's one way to read what this property is saying. And we'll see later why it's actually important to keep track of the parameter. So that's going to be my first property. My second is going to be totally different. So taking a step back and just looking at general functions from f2 to the n to r, which our Boolean functions are an example, we'll notice these all form a vector space. So we can start talking about orthonormal bases and inner products on that vector space. And I won't go into the details of this, but to make a long story short, you can put the following inner product on this vector space, which roughly speaking says, take the dot product and divide it by 2 to the n. And with that inner product, there is a very, very nice set of functions, which we call parity functions, that form an orthonormal basis. Now, because it's an orthonormal basis, we can start using a bit of a fancier language for it. We're going to call those functions Fourier characters. And the inner product of my function with a Fourier character, we will call it a Fourier coefficient. So given any Boolean function, you can write a unique list of 2 to the n Fourier coefficients that describe it exactly. What's the upshot of some of this? Well, one of the very nice theorems in Fourier analysis is something called Parseval's theorem, which says that if I sum up all of my Fourier coefficients, all the squares of my Fourier coefficients, this is exactly equal to the average value of my function squared. Well, my functions in this particular instance are plus minus 1 valued. So the value of my function squared is simply 1 at all points. In other words, the sum of all of the squares of my Fourier coefficients is exactly equal to 1. They're all squares, so they're non-negative, which means I can define a probability distribution for any Boolean function. I can define a probability distribution on f to the n, where the probability that I pick a specific value is equal to the square of the function's Fourier coefficient on that. We're going to call this distribution the spectral sample. And we can start talking about the properties of this distribution, and they will relate back to our quasi-random properties. More formally, what I'm going to do here is I'm going to look at my spectral sample on some certain structured subsets. So a subcube, C of SZ of codimension K, is going to be a set of the form of all X, which when restricted to the set S, give the exact same value C. And the size of S will be K to denote the codimension. So picture is worth 1,000 words. Here are 2 subcubes. In blue dashes, we have the subcube given by fixing the second coordinate to be 1 and letting the other 2 coordinates range. And then in red dots, we have the subcube given by fixing the first coordinate to 0, the last coordinate to 1, and letting the middle coordinate range over. So you should really just think of these discrete cubes sitting in the hypercube when I'm describing these things. If my function is chosen uniformly at random, my spectral sample should also be a uniform distribution. And so we would expect that if I give you a Boolean function that is quote unquote random-like, well, it should assign similar weight to any subcube as it would under the uniform distribution. So in particular, a Boolean function will have the spectral discrepancy property, SDK epsilon, if the probability under the spectral sample of landing in some subcube is very, very close to what it should be if the function were truly random. That's how I would suggest you read this property. So we have 2 properties, the balanced influences property and the spectral discrepancy property. I'm going to add on a third, and it will be something, again, completely different. So let's put Boolean functions to the side for the moment. I'm going to talk about colored multigraphs. So here it's a multigraph, which means I allow multiple edges, but not subloops. And I'm going to say that the edges are colored using a color set S. This is not necessarily a proper coloring. It's simply some assignment of colors to each edge. And now what I'd like to do is start talking about embedding graphs into these colored multigraphs in a nice way. So if I fix a colored multigraph with color set S, and I fix a simple graph, G, I'll say that G has a rainbow embedding into M if I can find an injective coloring, so I never use the same color twice, i.e. every edge gets its own color, and a graph homomorphism from my colored graph into the multigraph, which preserves my coloring. So once again, this is better explained by pictures than by words. So here is a colored multigraph. You'll notice I'm using the color yellow quite frequently. That is totally fine. All I'm using here are the fact that I can find a valid color. And then over on the left side, I have the tree K12. Now, what I've done here is I've colored the edges red and green and then mapped them to the appropriate vertices. And you'll notice that in these thicker edges, this is precisely my copy of K12 inside my colored multigraph. And so the rough idea that we're building up to here is we're going to want to count how often a specific graph can be embedded into a colored multigraph. And the specific colored multigraph I'm going to pick is going to be defined by my Boolean function. So I'm going to pick the example of the OR function. I've given the formula here, and I've labeled each edge by the vector over f2 to the 2 that will define that particular edge. More formally, given a fixed function, a fixed Boolean function, and a fixed k, I'm going to define the rainbow Hamming graph, RHG, K, and F. It's a colored multigraph, and its vertex set is the set of all vectors that have Hamming weight at most k. And the edge set is a little tricky. The way you should think of this is that I'm going to define my edges via, I'm also going to include the color in the definition of the edge. And so the specific formula here is that the color, I'm going to pick two vertices and let my color denote sort of a shift. And so if my function at the first vertex plus my shift is equal to the function at the second vertex plus the shift, this will be an edge with a specific color in the rainbow Hamming graph. Long story short, the definition is a little intricate, but it does, this is simply a nice example of a rainbow Hamming, of a colored multigraph. Now, what I'm going to do next, and this is the part that I find is a little interesting. I will fix a particular embedding of my simple graph G into my multigraph. And I'll define EM sub B, G into M, as the number of colorings for that specific embedding that give a rainbow embedding into G. My property is then going to be that a function has the rainbow embeddings property, rain of D epsilon, if this count of the colorings for each possible embedding is close to what it would be in a random graph, in a randomly chosen graph. The thing that I want you to get out of this definition is most of the time when we talk about embeddings of graphs, we average over all homomorphisms. We're not doing that here. I am picking a specific embedding, and then I'm saying you get to pick a bunch of different colorings to make this embedding work as a rainbow. It kind of boggles my mind that you can actually find any graph that does this, let alone the fact that you can do this for any possible nice embedding. You can find lots of colorings that work. So I've given you three properties: the balanced influences property, the spectral discrepancy property, and now the rainbow embeddings property. Our main theorem is that for any fixed d greater than or equal to 1, all three of these properties, and in fact 6 others, imply each other. That given a Boolean function, I can consider all of these different properties and up to small losses in parameters. It will possess every single one of them if it possesses at least one. Now, this is the equivalence theorem that I mentioned. We also have a construction theorem that provides explicit examples of these things. And this is where that parameter d is going to come into play. Because for each d, we can construct an explicit function that possesses the balanced influences property with epsilon equal to 0. In other words, this possesses every property in our main theorem with really good parameters. But if I increase d by 1, then my function doesn't have the balanced influences property or any of the others for any reasonable choice of parameters. In other words, we not only have a theory of quasi-randomness, we actually have infinitely many of them. In a towering hierarchy, each layer of the hierarchy stronger than the previous one. And this gives basically the end upshot of this is that quasi-randomness for Boolean functions is a much more intricate topic than it is for the case of graphs, for instance. And I'll mention as a final topic, these functions down here have some very interesting properties. Please ask me about them in the questions if you're interested. But otherwise, thank you for your attention. And I think I will end the talk here.
All right, thank you so much, Nicholas, for delivering that talk. Can everyone join me for a round of applause by giving a reaction clap to Nicholas? Okay. Does anyone have any question? Feel free to raise your hand, unmute yourself, or if you have any question and prefer to put in the chat, you're welcome to do so.
I don't have any specific question, not very, very specific. That's a very good walking presentation. It's very interesting.
Thank you.
And so you have multi-graph. Is the next step multi-hypergraph?
That is another great question. There actually is, so that is the next step. There is a version, some work that we're planning on looking into is a version of this that actually looks at hypergraphs. That basically looks at a sort of like the next step up in terms of influences. It's a little tricky to explain the exact relationship here, but there's the short version of it is that there should be another set of properties that basically look all like this, but now instead of dealing with graphs and 2 inputs as we did with influences, you can now deal with K inputs.
Yeah, that was my guess.
Yeah, the notation will probably be unpleasant to read, but I believe that there's something like this should be true, and there'd be some good reasons to look into it. Long story short, the functions that you construct will probably be cryptographically very interesting.
Yeah. Yeah. You can see crypto looming behind everything here.
Yeah.
Thanks.
Okay, thanks, Thomas. Does anyone else have any remark, question? Okay, if not, then please join me again, giving a round of applause to Nicholas